All right, Newton's laws, the first two laws, give us the answer to this question. It's at a constant velocity, therefore the net force has to be zero. So Newton's first law says that everything stays at a constant velocity unless there's a net force on it. So it has to stay at a constant velocity, that has to be no net force on it. And Newton's second law, F equals mass times acceleration, well, it's not accelerating because it's at a constant velocity. So that's zero. So regardless of the mass, the net force is going to be zero. That's probably not the problematic one. The problematic one is probably working out what the size of the braking force must be. Okay, so let's think about the forces that we know are acting upon the train. First of all, there's the weight force acting vertically downwards, and then there is the reaction force. The normal means at right angles, reaction force from the track up on the train. Well, it's not a reaction to the weight force, it's a reaction, it's not a reaction to weight, it's a reaction to the train pressing down on the track, and so the track's reaction is to push back up on the train. So they're the two forces acting on the train that we know about. But we know there must be a third braking force because otherwise, as you can see, that gives rise to a net force down the slope. So in order for the net force to be zero, there must be a braking force, and the braking force is going to be up the slope, and the braking force is going to be just enough to completely make the net force zero. So it's going to be that resultant vector that you get when you do a vector sum of the weight force down and the normal force from the train track upwards. So that means that the net force of the sum of those two must be equal to the brake force. Well, the brake force has to be equal but in opposite direction to that, so that we end up with zero overall net force on the train. And of course, cos theta is going to equal the force of the brake divided by mg, and from that we can work out what the braking force is, and in this case in terms of an expression. So just a quick note on action-reaction pairs. A common misconception is to think that this normal reaction force that I've drawn is the reaction to the weight force. It's not. So the weight force on the train comes about because the planet's pulling it down because of gravity. And so the reaction force to that is the train is actually pulling up on the Earth. No, the reaction force that's over here is because the wheels of the train are pushing downwards on the metal tracks, and the track's reaction force is that normal reaction force. So remember, when we're adding up the forces on an object, we're only worried about the forces on the object. So the only forces on the object is that force and that force there, but they're actually not matching action-reaction pairs. They're the reaction pairs or the action pairs on the train, ignoring the other objects.